There are multiple ways that we could present the second law of thermodynamics. I'm going to choose to present one that builds off the first law of thermodynamics and thinking about both of these laws in terms of an isolated system. So the first law of thermodynamics tells us that the change in the internal energy of your system is going to be equal to the energy transferred into or out of your system as heat minus the work done by your system. So again, you can transfer energy within your system one or two ways: as heat or through work. What does the first law tell us about an isolated system? Well, if your system is isolated, that means that it can't exchange energy or matter with its surroundings. And so if it can't exchange energy with its surroundings, then there's no way for energy to be exchanged as heat, and there's no way for your system to do work on surroundings, which tells us that the energy of your isolated system can't change. So delta E equals 0 for an isolated system. The second law of thermodynamics says that for that same isolated system, even though your energy can't change, your entropy can. So your entropy cannot decrease. Instead, delta S, the change in entropy, is either going to be positive or 0. It'll equal 0 if your process is reversible. So your entropy won't change along a reversible process. Your entropy will increase along an irreversible process. A reversible process is one that effectively can be undone. In proceeding from state A to state B along a reversible process, what that means is you know every single point between the state you started at and the state you finished at, and so you can go back through each of those states to get back where you started. The reversible process is an ideal process. In the real world, processes are irreversible. That in going from state A to state B in the real world, there is some fundamental change that you cannot undo with either your systems or surrounding to try and go back from state B to state A. This means that when you keep track of all the pieces of your system that are involved in exchanging energy within some thermodynamic process, that the total entropy of your system cannot decrease, and in the real world it will increase. Part of why I like this particular framing for the second law of thermodynamics is the story that goes with it. So Clausius was the scientist back in the 19th century that formulated the second law of thermodynamics in this way. And what he was looking for was a second law of thermodynamics that perfectly matched the first. He was trying to show that the entropy of an isolated system does not change in the same way that the energy of an isolated system does not change. But what he found, of course, is that that's not the way the world works. The way the world works is that when you let your system evolve, it moves towards a state of higher entropy. And if we think back to entropy being a measure of the multiplicity for a system, so a measure of the number of ways in which a system can be arranged in a particular macro state, what the second law of thermodynamics is really telling us is simply that the universe tends to be in its most likely state. So if given the chance, your system will evolve from state A to state B, increasing its entropy because there are simply more ways that its energy can be arranged in state B than what it had available to it in state A. If you think about all the possible states that your system could be in, the entropy increasing is another way of saying that you will find your state in the most likely arrangement.